Crunch seminar. Our first speaker today is Dr. Reza Ahmed. He would be talking to us about applications of machine learning in improving the assessment of myocardial remodeling in cardiac diseases. A little bit about him. Dr. Reza Azaz is an assistant professor and the director of computational cardiovascular bioengineering laboratory in the Department of Biomedical Engineering at Texas A&M University. He earned his PhD in mechanical engineering from the University of Pennsylvania in 2014 in the area of constitutive modeling of soft materials, and his postdoctoral research focused on cardiac biomechanics. Dr. Azaz Group's primary research interest is to integrate medical imaging with cardiac biomechanics and modeling to advance the understanding of myocardial remodeling in structural heart diseases and develop image-based technologies to improve non-invasive diagnosis and prognosis of these diseases. With that, please join me in welcoming him for the presentation. You may want to start, Professor.
Well, thank you very much, Samdata, for the wonderful introduction. So let me just go ahead. You see the full screen, right?
Yes.
Yeah, very good. Yeah, thank you again. So yeah, as Samdata was mentioning, my name is Reza Avazmohammadi, and I'm an assistant professor in the Department of Biomedical Engineering at Texas A&M University. And I'm going to talk about basically how we can leverage medical imaging in the context of cardiac diseases and the routine clinical measurements using machine learning to be able to improve assessment of the cardiac function and improve the prognosis and diagnosis in these diseases. So my talk, I'm going to basically focus on the application side of the machine learning and not going through a lot about the methods. So it's basically we are having some measurements, clinical data, either from the animal or human, and then how we can use machine learning to find out from these images something that cannot be easily basically extracted, but the machine learning helps us to extract those data that can improve the assessment of the cardiac function. So, and yeah, please feel free to interrupt me at any point if you have any questions, as Samdata was mentioning. So just a few introductory slides. So most of the talk is going to talk about focus on the myocardium, which is the functional muscle of the heart. Basically, myocardium contracts and then the heart pumps the blood, right? And a lot of diseases are related to the impairment in the myocardium, right? So this slide basically shows the schematics of myocardium. So you have the organ here. And then, there is an architecture in the myocardium. And at the tissue level, you see this architecture. Basically, there are fibers. And at the cellular level, you can see that this aggregate of the fibers, so basically those green strands are the fibers. And then, there's extracellular matrix as well that maintain the integrity of that network that's shown with the pink color here. So fibers contract here, and there is a variation in their architecture across the thickness of the muscles, and because of that variation, there will be some also twisting of the tissue, and then overall that leads to the pumping of the blood at the organ level that is characterized, for instance, how much blood is pumped through ejection fraction, etc. So it's basically what I described, just a very basic mechanics of how the heart works at different scales. And then the impairment in myocardium can take place at different, again, length scales. You can have the cells that dying here at the cellular level, or they will be hypertrophy. The cell becomes smaller, bigger, change properties, right? And that impairment is going to upscale at the tissue level and then basically show up at changes in the function at the organ level, right? So what I'm going to focus on is that a lot of clinical measurements focus on this scale, right? So you have the characteristics of the cardiac function, and they basically characterize what's called the organ level assessment, organ level metrics, right? And those organ level metrics can say only so much about what's going on at the tissue level and also at the cellular level, right? So those cannot be very too sensitive about the changes at the lower scale, right? So we basically are seeking the the possibility that with machine learning integrated with imaging, we be able to tell more about the changes that happens at the lower length scale, particularly tissue level and cellular level. So this basically summarizes what I just said. So on the top row, we see I've basically labeled it as a conventional biomarker. So you've got basically the MRI of the heart from which you can calculate the displacement. That's basically the strains, and then some basic measurement through catheterization of the chamber. This is the pressure volume. So you increase the pressure, you increase the volume, and there is a pressure volume that is a very basic characteristic of the ventricle. So these are the standard measurements. And sometimes if there is an acute injury to the heart, so that there is a certain protein that is released and changes the content in the blood. So that if you have a blood draw, they can measure that proteins as well. So these are some very conventional markers that that they use in human, right? So everything's in vivo. So we don't have, for instance, access to the tissue, but we have access to some function that we can measure through imaging and catheterization. So these are obviously going to be limited. So we get basically limited information from them. On the bottom row, I'm showing what possibly we can get from an animal model of cardiac disease. So you have a animal model here, a mouse, for instance, and then we can do this measurement at any point, and then you can sacrifice the animal and harvest the tissue. So once you harvest the tissue, then you actually obviously have the access to the tissue, so you can go see what type of changes happens in that tissue. For instance, there is increase in the collagen content, changing the properties, changing the architecture, and then you can put all those information together and produce something called in silico model of that animal, and then study further. For instance, if you do other changes, how they change the function, right? So these are basically, I'm drawing the contrast between these two type of measurement that we can have, right? So in the bottom, you have the luxury, actually you have the access to the tissue and you can do a lot of measurement. So the question I'm posing is that, is there a possibility that we can use the information that we have in the top row, but at the same time, get some of the important properties at the tissue level, something that that we can also validate in case we also have access to the tissue level as a ground truth, right? So again, this is the one particular problem I'm going to discuss now is the myocardial stiffness, right? So in this basically case, a lot of diseases, for instance, diastolic dysfunction and different cardiomyopathy, or just aging, right, changes the stiffness of the myocardium. And then when the stiffness, which is basically the mechanical property, very important mechanical property of the tissue, when that changes, the systolic and diastolic function of the heart is going to change, right? So currently there is not a standard way to measure the stiffness of the tissue. What's available is that we can measure something that from which we can infer what has happened to the tissue. So that's called, like, for instance, organ level pressure volume measurement. So you have a chamber, you put the pressure, the volume goes up, right? If the stiffness changes, that pressure volume measurement is going to change, right? So that's going to indicate something has happened in the tissue, but there is other things that could happen that collectively, basically lead to the change in the pressure volume. So that pressure volume measurement per se cannot say exactly what is, the intrinsic changes in the properties of the tissue. In contrast, if you have the access to the tissue, you can obviously measure in the lab what has, and measure the properties. So what we are trying to do here is that use this organ level pressure volume measurement integrated with machine learning, and to be able to estimate tissue level intrinsic stiffness. So what we do, we actually had several animal models, about the 40 animal model, mostly rats, and these are basically from some major diseases, pulmonary hypertension, myocardial infarction, and several of them were just a control. So we had the images from those animals. We basically reconstructed the heart, and then we had also the architecture of them, and we did the finite element simulation. And for each animal, we developed this pressure volume measurement, right? So in finite element simulation, when we do this, and then we have the inverse, we can do the inverse model. So once we have this pressure volume measurement, for instance, we can, and then we have also the geometry and architecture of the animal. So we can set up an inverse model, and from this pressure volume measurement at the organ, determine the properties of the tissue, right? So that's the inverse model. But, doing this for each animal and then, in the basically clinical setting is going to be not feasible, right? Especially if someone who wants to do this who actually doesn't know about, the technicality of the finite element and wants to use something simple to just obtain the tissue properties. So what we did is that we basically had those animals, about 25 animals, and then we generated additional hearts from them. So I'm showing it in this graph here. We basically did resize the ventricles, both right ventricle and left ventricle. And we also have just a different, what I call the parent geometry. So each parent geometry, we created the other geometries from it. So overall, from each parent geometry, we created 100. And overall, basically, we had 2,500 geometries. And we also synthetically change the fiber orientation, and we consider every possible fiber orientation you can have in your heart, and then we also changed different pressure waves, right? So basically, going from 0 to 30 millimeter of mercury, we put that in each ventricle, and then we produce this pressure volume measurement. So we created this database that covers a good span on geometry, architecture, and load, right? And then we train that. We basically perform finite element simulation for each single of them, right? That comes basically from the, again, pressure volume simulations. So we have basically the geometry, fiber orientation, excuse me, and material, myocardial properties. These are the geometry, fiber orientation, and EDP-VR as input, and myocardial properties as output, right? So we use just a basic artificial neural network to train on this database. And then at the end, what we have is that, here, I'm going back to this slide. So very basic measurement of the geometry. So somebody has the images, can go here and look at the shortest slices of the MRI and measure these areas and measure, and also the volume. So these basic geometric metrics can obtain from just basic standard MRI, right? And then you have also pressure volume from catheterization. EDP-VR is called end-diastolic pressure volume relationship. That also comes from catheterization, right? So you have the basic measurement of the geometry. You have, also the architect. For the architecture, all you need to know is the helicity, like how steep the architecture changes across the thickness. And then you have the catheterization, and then you, using the machine learning, basically you get the property, the stiffness of the tissue. So we use the, a constitutive model that has the property of the tissue AF, PF, and then, we use basically, we validated, we did the training and then the validation. There are some, some consideration about the identifiability of the parameters. I'm just going to skip that in the interest of time, but these are showing basically the final results that we did for those properties, AF, PF. And then, we did the worst AF, best VF comparison, and then, the worst one even didn't matter much in terms of if we want to just create the stress-strain relationship of the tissue, right? So at the end of the day, we have this feasible pipeline that gets geometric parameter directly from MRI and pressure volume measurement directly from catheterization. So someone put them in the machine learning model, and the output is going to be the tissue stiffness, right? And then we also did, this is the sensitivity we did. So, we have several geometric parameters, and we did the feature importance and just see which of them is, more important. So the LV volume and LV area happens to be more important. And we narrowed down the parameters. And then EDPVR, we have, that goes from 0, again, to 30 millimeter of mercury. So the closer the part of the EDPVR, the closer to the 0 pressure actually happened to be more important. But anyway, this was the feature importance to just narrow down the number of parameters needed to estimate the properties.
Hi, Reza. Hi, this is Milan from Johns Hopkins. I have a couple of questions. Can you go back to your the slides that you show your machine learning data set?
Data set?
No, the previous, yeah, this one. Yeah. So how do you generate the fiber orientation? Rule-based methods?
Right, rule-based.
Okay.
So basically we just constrain the fibers in all the mammals that has been studied. Basically has a negative slope from endocardium to epicardium. So that's the only constraint we had, but then we had every possible angle.
I see, because the reason I was asking because we also do this rule-based method to generate the fiber, and we just fix the fiber orientation for different patients. So and we compare, like there was a paper that we compare our rule-based method with fixed fiber orientation with a DTI
so
what's tensor imaging, and it seems pretty match up very well. So I'm not sure, like the variation in the mouse, the fiber orientation in the mouse. So is it does that vary a lot or no?
Across thickness, yeah, it
Okay.
varies. Endo is going to be, for instance, 30-40 degree, and then epi is going to be -40. So it has a usually variation about.
Okay.
Yeah, turn mouse. And
okay.
What's important is that once we actually did the feature importance, and here what I have is theta AP, theta endo. Those are two fibers that you need to put in the model. At the end of the day, did not matter a lot, right? Mm-hmm. So the stiffness. So if you have, think about it, you have a chamber, you put the pressure there, and you get some volume, and then keep everything the same, but only change the architecture, change the helicity a little bit. You pretty much you're going to develop maybe similar pressure volume measurement. I mean, if you don't significantly change the fibers. But so yeah, that's what one thing at the end we did is that we also compare our result against the ground truth, which is you actually harvest the tissue and go to the lab, actually do the experiment and measure the stiffness. So that's what matters after all, that you actually measure the stiffness with the experiment and see if the machine learning agrees with that. So that's we had a good agreement with one case that we did use those. We had the images and all those parameters, so we fed that to the model, estimated the property, and then compared against the tissue for the same animal that was tested in the lab. So that was basically in a nutshell like what I wanted to cover there. But one thing you may notice is that I had only one for the properties for the concept modeling of the myocardium. I had only one fiber family, right? Whereas in myocardium, you have myofibers, which are basically contractile part of the tissue. And then you have extracellular matrix, the collagen, which is important in the healthy tissue, but also becomes a lot more important in the disease tissue that you have, for instance, fibrosis, and then the increase in the collagen content. So we upgraded our constitutive modeling, and you can see here also again schematics of the tissue, sort of a representative tissue element that you have those muscular part, and you have also then the collagen part. We upgraded our concept modeling, included two fiber terms, one on myofiber and one on collagen, right? And then there is discussion about like at what strain which one actually becomes dominant. At the lower range of a strain, myofibers are more dominant. The higher strain, the collagen are more dominant. So that adds, for our basically purpose here, that adds two additional constants here. And the collagen usually is undulated. So we have to also account for that undulation stretch here. So we have, long story short, we have more parameters now, right? So additional input that we can add is the strain. So that's something also clinically is available. We basically have MRI. You can do image registration, and for each pressure, you can measure the strain in the myocardium. So we added that one because now, on top of everything else, we added also the relationship between pressure and the strain in the finite element simulation for each the heart that we did. We included a strain as well. And then, we did, again, the similar modeling and the comparison between predicted and actual. So the translational value of this is that, so we have here the properties that represent myofiber and the properties that represent collagen, right? A lot of cardiac diseases, you have a pressure overload in the ventricle that remodels the tissue, okay? Basically, tissue remodels itself to be able to cope with that increase in the pressure overload. And that remodeling includes changes both on the collagen and myofiber, right? And so then when we get the stiff tissue, could be your myofiber is stiffer, could be you have just more collagen, but it's not clear. If you look at the images, you cannot tell 100% what's happened, right? But therapeutically, it's very important because if you want to target myofiber, you have to do something. You want to target collagen, you have to do something else. So it becomes important to separate those from the images. And for each patient is, again, it's different. So you have to see how much collagen has changed, how much myofiber have changed. So basically this, that has a translational value of this approach here. So I want to switch the gear a little bit here, as basically included in my abstract, I'm going to talk about different diseases a little bit and how we use machine learning in each setting to help with the determination of some properties of myocardium. So myocardial infarction or heart attack is a leading cause of death in the US and also is a very critical, basically, disease worldwide. And what happens is that due to the coronary artery disease, a part of the muscles actually is lost. So it does not contract anymore. So you get a plaque here, and then the blood cannot be transmitted to the muscle. And once that happens over the course of an hour or so, actually the muscle is lost. And then from there, there will be a scar formation and at the site of injury, and then remodeling of the ventricle, right? So one very important measurement for someone who has had infarction, heart attack, is that to determine what is the extent of that infarction, and where's the location of that infarction. So that basically you risk stratify the myocardial infarction MI patient. The current way to do that is using what's called late gadolinium enhanced MRI. So this is the basically you have a standard MRI, but then you inject gadolinium into the patient, and that gadolinium and goes basically what happens that attach the scar. So if you have a very mature scar, that shows up in MRI with the highlighted area. So in the MRI, it shows with the highlighted area. Obviously, if you harvest the heart and do the histology, you can see that obviously as a scar formation, the deposition of the collagen, etc. But in vivo, when you have only images, that's what's done. And there are limitations with this gadolinium. So the scar has to be mature enough to show up in the image, and also not everyone can receive that. There is also some risks involved with the patient that have kidney problem, and also is limited to MRI. So if you do ultrasound, you cannot get that. If you do CT scan, you may not be able to get that, right? So another way to look at this is that, okay, so I've got myocardial infarction here, and what happens is that this part of the heart does not contract. During the cardiac cycle, this part does not contract. So what happens is that there's definitely going to be a significant changes in the strain of that part that is not contracting or is like subcontracting, right? So it has suboptimal contraction. So why don't we just look at, instead of doing late gadolinium enhancement, we just, whatever imaging modality we have that a lot of them actually can give a strain at this point, like ultrasound, CT scan, and MRI. All of them can get a strain. Why don't we just look at the strain and see where we have impaired the strain, and from those impaired strain, we basically determine the location of the infarct, the extent of the infarct, and possibly the stiffness of the infarct. And that becomes important because throughout the remodeling, the stiffness of the infarct changes by scar maturation. So that's what we did here, again, using the finite element modeling. And then we created this database that we changed the infarct, we synthetically generated infarct in the finite element and changed it as many possible ways, the location of it, the extent of it, the stiffness of it. So we created big database and then they trained the A&N again for the classification. So here you see, for instance, we have different infarct location and then we changed the geometry as well. So I'm just showing, and we also had those coming up from the animal models that, basically we have a rodent model that you can collect the hearts at different time points, right? 1 week, 2 week, 3 week, 4 week MR. So we had this animal model and we used that as a parent hearts, but then we built on it to create more hearts to have a larger database. So here, based on this, there is a standard way to present the strains in the heart, and that's called AHA segmentation. So this is bullseye plot, and then, basically segments the heart. I think I had it in this. You can see that basically you do the short axis slices of the heart, and each one gives you this little donut, and you put them together and you get that bullseye strain map. So for each finite element, we created that bullseye strain map. And here, basically, I'm showing an example of it. Sorry. That you can see in the circumferential strain, radial strain. So circumferential strain is supposed to be negative during contraction. So obviously, when you see something like that, it doesn't look good, that you have this positive circumferential strain at the end of systole, which is the highest, you expect the highest contraction. Radial strain is supposed to be positive. So, there is also a little bit of change here. I think the numbers are cut up here, but you can see again the changes. The radial strain is supposed to basically show negative here, and the the longitudinal strain also. And here basically I'm showing an extreme example where the strain changes in the strain is very evident, right? But the data we had, not all of them was like that. So we had a variation of how much change in the strain we get. So we put them together, and this is also showing some, we wanted to make sure that our strain is sensitive enough to the location of the infarct. So we did some of just the correlation, synthetically did the correlation study between the percentage of the infarct and then the different strain measures, and also the stiffness and then the strain. So that becomes also a parameter if you are interested to also estimate the stiffness from the strain, right? And we have the full strain map, right? So the strain is basically a 3x3 matrix, has normal component, has shear components. We have all of them, but clinically they're usually represented only through this anatomical direction: circumferential strain, radial strain, longitudinal strain. So we use those to train our model. Again, we just use the basic A&N classification model, and I'm showing just a representative result here through this confusion matrix. And then we basically, we did, again, that segmentation of the heart, and we evaluated and inspected each segment based on the strain, whether this segment is infarct or not infarct. So we already have the ground truth through our synthetic generation of the data, so we can tell, basically compare them and just see how much, we had the correct answer of whether infarct or non-infarct. But after all, we had a good accuracy of identifying infarct location. And here, just a very brief results on that. So that was. And I'm sorry, I'm actually switching a lot between different topics, but in different contexts, we've used, all of them are basically, structural heart diseases. And the commonality between them is that how we can use this machine learning to, again, estimate some tissue level properties. In the infarct part was the stiffness of the infarct and also just the geometry, identification of it. Where is it in the ventricle, and how big it is, right? A similar topic is pulmonary hypertension. So infarction focuses on the left ventricle of the heart, right? So usually people get infarction in the left descending coronary artery. But there are also some structural diseases in the right ventricle of the heart, and that's what I'm going to talk about here a little bit. So you have the pulmonary hypertension, the hypertension that's induced by the pulmonary vasculature, and that, you know, there are certain classes of that hypertension pressure overload can be caused through different sources. It could be idiopathic entirely, that, you know, for instance, that the source is not known. That's the first class. It could be through some lung diseases. It could be through diseases of the left ventricle. But overall, you have some pulmonary pressure overload in the right ventricle. And what happens, right ventricle is actually a lot thinner and floppier than the LV. So if you put the pressure overload on it, it can remodel quite fast, and it can remodel significantly in terms of changing the properties and in terms of changing the architecture, right? So you can see here in the animal model, for instance, in the left, you have the normal right ventricle, but then you see that there's a dilation here, significant hypertrophy of this tissue. And again, that could come from fibrosis, and could come from, you know, the hypertrophy or just changes in the thickness of the myofibers, right? But the tissue becomes a lot stiffer. So what I'm going to show here is, for instance, some of just ex vivo tests we did for the tissue from control animal, normal animal, and for the and the tissue that from pulmonary hypertension rodent models, and, you know, basically we can see significant changes in the properties, in the stiffness, and if you do the constitutive modeling and determine how much is due to myofiber and how much due to collagen. I have just some representative results here that shows this is the stress strain measurement. So you have the control, and then, you know, there is a modest increase in the stiffness, in the stress value for myofiber, but there's a significant increase in the pulmonary hypertension. So our interest here is going back here. Again, the stiffness of the tissue is not something we can feasibly measure in vivo, right? You can measure pressure in the ventricle, and with catheterization, we can measure different echocardiography metrics, like pulmonary, basically PAT, pulmonary acceleration time, and, you know, TAPSI, RVSP, etc. So there are several echocardiography indices we can get, and also the index that come from catheterization, or, you know, that pressure, right? So the idea is whether we, you know, if we can use those metrics to estimate tissue properties, right? And here, what we use, you know, we use a little bit of physics-informed neural network modeling, and I'm gonna very briefly talk about it. So we had animal models of pulmonary hypertension, and we had several animal models. We had the mild pulmonary hypertension, because you want to basically develop this spectrum of stiffening or changes in the properties. Mild, the hypoxia, basically the animal is in the hypoxia chambers, and that's how the pulmonary hypertension is induced in animal. And there is also severe pulmonary hypertension, that when the pressure overload is a lot higher and the stiffness is going to be a lot higher. So we had those measurements for those animals. So we had the echo data, pressure data, as well as the ex vivo tests on the tissue. So we had the ground truths that actually what happened to the tissue after all, in terms of the stiffness, changes in the architecture, etc. So through the histology, that's what we can measure the structure. So here I'm just showing there's some representative echo data, PAT, and TAPSI and thickness. And then we did the stress strain measurement ex vivo for them. We have hypoxia, which is the mild pH, and the Sugen hypoxia, which is Sugen hypoxia is basically you have also Sugen injection in animal before it goes to the hypoxia chamber. So that actually damages capillaries in the pulmonary vasculature, and that's what leads to severe pH. And you can see significant stiffening for the Sugen hypoxia to that is like 80 kilopascal. Here is like 40 compared to hypoxia, and then the stiffness increases definitely. So we have this good range from control to mild pH to severe pH. And then, obviously the stiffness is going to correlate with the RVSP, right ventricular systolic pressure, and then, with PAT, pulmonary acceleration time. So we put that, our again interest is that for the same animals, we have the tissue test and we have the hemodynamic data test, and we put them together, right? And then we include this concept modeling through this physics-informed neural network. So basically, hemodynamic values here refer to all of those hemodynamic data, pressure and echo. And then these are the deformation metrics invariants that come from tissue tests. Where I invariants are basically the deformations that they characterize the deformation that we apply, the biaxial testing that we do in the tissue. And then on the right-hand side, these are the energy, but then we include the energy terms here, right? So these are constrained. These energies basically are constrained by producing the same stresses, right? So basically we have these stress measurements, a stress strain measurement, and then those invariants are basically are different metrics of these strains. And then we fit, using this concept of modeling, we fit to each stress strain measurement. So we have those properties, right? So as sort of our ground truth properties. But once we put those properties here and estimate the energy, and then we take the derivative of energy to find the stress, that stress has to match also to the stress that we've measured just ex vivo, again, our ground truth stress. So that's how we've involved this concept modeling within neural network. And, that's the part we say, basically that I refer to as physics-informed neural network. And, that basically they have the total loss. The rest of it is just basically finding the error between the experimental part and the neural network part. A disappointing part here is that, let me just include also say, so basically because we have about 40 animals, and so we are using leave one out cross validation here, basically devoting one sample to tests and one to validation, and the rest of it to training, and then we repeat that for each sample. So we have they have a sample size of n, so we have the n iteration of that. So this is a work in progress. So all I have now is just the fit we did so far to the experimental data, but we have the setup. We hope that we actually get a good results here. So the end product would be for these animals, we have this PIN model that at the end of the day will use only the hemodynamic data to estimate the properties. So that's what we are aiming for. So that was pretty much what I wanted to cover in terms of cardiac. I have just a few slides that I can go pretty quickly, is in the context of lung biomechanics, and that's something also very important. Here, these are just a few slides that can go in a few minutes. So I'm just switching gear now to lung, and then what happens in the lung, and when basically there is a lung injury. So people develop this ARDS, acute respiratory distress syndrome. A lot of COVID patients basically have ARDS, and then they need to go to hospital and get basically ventilation, mechanical ventilation. And that mechanical ventilation in itself actually can deteriorate the lung injury if it's not done properly, right? So what I'm showing here is you see the alveoli in the lung. So basically in the natural respiration, so you breathe in, you pressurize these alveoli, and then you have the expansion of them, and at the expiration, there is a de-recruitment of them. So basically, they depressurize till the next cycle, right? So there, if these are over-pressurized, right? So the volume actually goes up. So that's called volume trauma or barotrauma if you have an increased pressure or increase in the volume. They can be actually overstretched and injured. On the other hand, if you don't have enough pressure, right? So you actually almost produce the vacuum in them. They are de-recruitment. And if you do that enough, so basically they are entirely depressurized, so they collapse, and then they basically expand again and they collapse. That also can lead to the lung injury. So there is a sort of a, sweet spot that ventilation needs to happen there to avoid both volume trauma, barotrauma, as well as atellect trauma, which is the recruitment of the alveoli. So there is not a good understanding of what actually drives this, right? What biomechanical factors in the alveoli drives this? There is a good hypothesis that if the wall stress in the alveoli wall, this is called basically alveoli septal wall, right? This septum, and there is a surfactant here that also helps with keeping the alveoli open. If the wall stress at the alveoli goes beyond certain values, that's where the injury takes place, whether we do volume trauma or atellect trauma, etc. But, as you can imagine, given the architecture of the lung, there is not an easy way to estimate septal wall stress in the alveolus, right? So here, another basically opportunity to use the machine learning. So we have the lung images. This is for the rat, and then we can get the deformation at the lung at different points, right? And for the same rat, we have the ex vivo CT scan, and then we can reconstruct a cube, what we call representative tissue element. And you see basically here, those alveolus here, right? So we have the deformation that comes from the image. And let's say, we have the architecture, more or less a template of architecture. So we can apply that here on the tissue and basically estimate the septal wall stress, right? But for the entire, if you want to do for one cube, that might be doable. For entire lung, that's not, something that, it's basically 4-dimensional lung motion. That's not feasible if you want to do it real time, especially, the ventilation is something that you need basically take care of it, accurately. So we basically did the machine learning here. In the database of, in the space of deformation, we have lambda 1, lambda 2, lambda 3, which is different. These are the principal stretches. And we did the hypercube sampling to apply those stretches on the cube. So once if the cube out is fixed and we did the training on these stretches from the image registration, at any point, once we have the stretches, we have, using the machine learning model, we have the stress, the maximum stress, principal stress right away, right? So we don't need to do finite element simulation because we've done that already and done the training. And again, this is we have very preliminary results here. We've done all 300 simulations, so we are basically aiming to do more here, obviously. But that's again the direction goes. But the final product is that we have the images. This is the in vivo images of the lung using the image registration. We have the deformation, and from the deformation we estimate the stress, and then we can basically see what are the areas that are at the higher risk of the injury, right? And if the ventilation, if we also add the ventilation, for example, the ventilation has different, you can use different pressure wave, right? If you use this pressure wave versus this pressure wave, how that's going to change the stress in those areas, right? So, ultimately in real time, you can optimize the pressure wave based on, the patient data that you get. So that's, I think, all I had. I mean, in summary, what I try to convey is that image-based cardiac computational modeling integrated with machine learning can quantifiably linked between organ level response to tissue level remodeling. So that's the link that I try to capture here. From organ level, whatever we can capture in the organ level, how we can use that to estimate what we are interested in at the tissue level, which basically contains the information what has happened to the tissue, what type of damage has taken place. So there is a lot of potential and a lot of opportunities, and eventually those metrics can be used as earlier stage markers for basically improving the diagnosis and prognosis in diseases. The work that I did was not possible without the especially the animal model collaborators that I had, Dr. Chaudhuri at Brown, Dr. Reza at Penn, and Dr. Smith, UC Denver, and a lot of animal data that I showed basically come from their lab. With that, I would like to thank all of you for listening to my talk for this time, and I'd be happy to answer any questions.
Thank you, Dr. Reza.
Sure.
Can I ask a question, Reza? I had seen some data before for pigs that show that the stiffness is different during diastole and systole. So I think it's twice. The modulus of elasticity was twice. If you take the average over one cycle or over the other. Have people consider that instead of having one uniform value throughout this cardiac cycle?
So I think the way we basically decompose it is that in the diastole, it's just the myocardium behaves just as a passive tissue, right? The activation hasn't taken place yet. So in diastole, it's just more or less is a passive tissue. In the systole, that's when there is electrical basically activation of the tissue, and then there's active force.
Right.
So if we combine active force with passive forces, and we basically there is going to be effectively a stiffer tissue.
Right. So twins are stiff. That's what I think it's the experiments for pigs that I have seen.
Yeah. Another way to look at it is just we say we're interested in passive properties as well as active properties. So that's that we can then we can combine them together and then have effective stiffness at any time point.
But you do have the active stress component in your...
Yes. So that's important to produce that contraction here. Otherwise, I cannot get, for instance, in this simulation I'm showing here, this contraction that you see in the ventricle, that's because of those active forces, right? So there is a dilation that's just like a balloon expanding, just passive behavior, and then there is active force added. That's how it contracts.
Right. So what is effective stiffness? It is the sum of the active and the passive.
Yeah, that's how usually common. Basically, active forces plus passive forces.
I see.
But it's just a more like modeling. So it could be not. There are also there are different school of thought. So people do decompose stress. There are people decompose deformation gradient. FEFA, LS, and then there is also models that decompose both of them, decompose the stress and also decompose the deformation. But yeah, this is not like basically the activation is what really make cardiac tissue different from other tissues like orthopedic tissues, musculoskeletal tissues. And you may not be really concerned about the active part, but the cardiac tissue, the active part is a big deal.
Okay. Also, I have another question on the possible misspecification of model misspecification, because you're using one model. I know that model is pretty good, but we work with Jay Humphrey, so we'd like to use his models and so on. Are these models, is there a model uncertainty here, or because you generate a lot of simulations and there's a lot of effort there. So if you have a model wrong, not wrong, but misspecified, let's say.
Yeah, yeah, that's there is a whole business stuff basically on some quantification of how much actually model contributes to that. And what we did that might not be like, you know, the most rigorous way to do it is, so there is this Fong model, and a lot of soft tissues, you know, Dr. Humphrey, for instance, uses that for the vasculature. I'll use this Fong type model. One way or another, it's a Fong type. You have invariant and then, you know, properties. But there is a good amount of basically covariance in the model already. So if you basically have something you want to fit to, it can fit with different set of properties, right? So we had this pressure volume measurement here. So we fit to, you know, from different initial guess from the blue line and the red line. And both of them happen to actually fit to this. But as you see here, they give very different properties. A here, this, AF this, and then AF this. So with different set of properties, we fit to the same experimental data. So there's also, you know, the model already has covariance between the properties. They're not uniquely determined. So what we did just basically decrease the number of unknowns. So we said, you know, for the metrics part, because it does not contribute a lot, so A and AG, BG, which are the ground metrics, we kept those constant, and we only basically estimate the AFPX. So that way, we reduce how much uncertainty we can have. But as you have said, I mean, you know, one person needs to actually look at different models and see, you know, study the differences and the contribution of those.
Okay, thank you.
Sure.
Minlan has a question, right, Minlan?
Yeah, I do have a couple more follow-up questions. Very nice talk. So I want to follow George's question. So I wonder what kind of imaging modality you can use in application, Cine or 4D MRI. Because for Cine, you don't have that much slice along the long axis. 5, I would say, is a typical number for human. So which makes your measurement data sort of sparse. So yeah, I wonder if your model can do that based on sparse data.
That's a very good point. So we use actually Cine MRI. As you said, for human, we can get something usual, a slice number of slices, we get 6, 7, 8, 9. The slices cover from apex to base. So that, what I'm going to say is relate to a different type of research that basically we have actually done it in my lab. We use what we call the super resolution reconstruction of MRI. So what we do is that we, this algorithm that basically improves the identification of the pixel that go out of plane and interpolates between the slices, right? So that way we can improve actually the estimation of, you know, on those slices, you already have pixel movement, so you can get the strength. The question is what happens between the slices, right? So if we have a good interpolation and that we try to do through this super resolution reconstruction, we can actually have a good estimate of the whole 4-dimensional cardiac motion. So that's the, you know, that's another realm of research, how to improve the quantification of motion through this limited acquisition of data through MRI. In 4D CT, in contrast, you have the voxel-based motion. In what I showed in the lung, that was CT. So there you have, it's very different modalities. So you get voxels, and for each voxel, you actually have the displacement of that voxel. So things are a lot easier. So it's not a slice anymore. You just have voxel in entire. If you get it right, you have the 4D displacement right away.
I see. So so for patients with fibrosis, if you want to do this interpolation between these slides, so there could be some difficulties, right? Right. So just assume, yeah. So
yeah, I mean, with fibrosis, so definitely you're gonna have different, you know, intensity in your image, but you know, it depends on what other information is available. You know, what I had in myocardial infarction, part of it is that basically, but you know, that's when you have a scar in your tissue. But yeah, but it's still doable. You know, it's image registration. Yeah.
Oh, sorry. One last question. So, you can you go back to your previous slides where you showed the catheter measure the pressure in yes,
like that.
So I wonder where you measure the pressures, in the RV or LV?
So what in the first?
Oh yes, this one in the middle.
Yeah. So it depends. Like, when the first talk I talked about everything was about the LV, the left ventricle.
Yes.
And then the pressure comes from the LV catheterization, and then the second the last part was pulmonary hypertension. That's RVSP, right ventricular systolic pressure. That's called right heart catheterization. Then that's the RV pressure.
Yeah. My point is, so if you want to measure the LV, you have to do the transeptal puncture, right? So just basically puncture at the septal wall and then put your catheter to the LV. So that's kind of a difference.
Right. So
pressure. And there's a difference between LV and RV. So I just want to
right.
double check. Yeah.
I think the catheterization, the LV is more challenging than the RV. Yeah. But in the animal, typically what we did is just a very small puncture at the apex. I mean, obviously you cannot do that in human, but a small puncture at the apex. So the catheter just goes through this little hole here at the apex. In rats, that's a common way to do the LV catheterization. But yeah, yeah.
Yeah, thank you. I don't have further questions.
Do we have more questions for the speaker?
Yeah, may I ask a question?
Yeah, you may. Please go ahead.
Yeah. So very nice talk. Thanks a lot.
Sure,
So my question is, from here, for example, I can see that you guys can measure the microstructure, information of the tissue, right? So, but maybe you mentioned that, but maybe I missed that. So in your model, is the material treated as homogeneous or heterogeneous? Is this microstructure information, besides the orientation of the fiber, like, for example, the orientation of the fiber, does that vary in different locations of the heart?
Right. So there is what I showed, I think the first one, is basically, I probably did not show the experimental data for that. What we call is helicity. So there's a variation of fiber orientation across the wall thickness. And that's actually very important parameter for the heart function. A lot of disease change that helicity, and that's why one way actually the function is impaired. So we measure that variation. If that's the heterogeneity in architecture, but if you're asking about heterogeneity in properties, for the ones that I showed, no, we basically have homogeneous properties, like AF, BF, etc. Those are the same everywhere.
I see. Yeah, so I'm curious, like say for the in vivo case, is that possible to also measure this microstructure? The
current state of the art modality is diffusion tensor imaging, and people are still improving it, so it's not rigorous yet for clinical work. But once you have the heart ex vivo, you can do diffusion tensor imaging. That gives a very good actually architecture. But in vivo, the sequence is not yet in the clinics.
I see. So basically, you can still have some data, but still not for clinical.
Yeah. It's a lot of work I think is in the research still, but I don't know a lot of centers that do diffusion tensor imaging of human, because there's a lot of artifact, with the heart motion and all that. They do it in the brain. If you look at all these neurons architecture in the brain, images, beautiful images, those are diffusion images because obviously brain doesn't move, but in the heart has a lot of artifacts, but as people are trying to improve their sequence.
I see. Yeah, thanks a lot. Yeah, and so also another question is, since we also work on the kind of the biological tissue, trying to do the mechanical testing and do the modeling of that. I'm wondering, like, is the paper, the results you present here, is that published? And also, is the data published? So maybe we can try to compare, use our methodology.
Oh, yeah, I think this is published. I probably have not. Sorry, I have not included the citation. The first one I showed you is it's Scientific Reports paper 2021.
Oh, okay. Yeah, I will try to.
Yeah, you should be able to find it under my name. Yeah. I
see. So the data set is also published together with the paper.
I think, yeah, if you have a limited data set, we've included there, yeah. But feel free to email me if you need anything else that I can point you to. Any data that you think can help you.
Oh yeah, that would be fantastic. Thank you so much.
You identify yourself because we only see half of you. So can you say who you are and where is your university?
Okay, yeah, I'm Yu. I was originally from the Crunch Group, and yeah, I now work at Lehigh University. Yeah, we also work on the tissue modeling. So we are interested in the cardiovascular diseases, such as the fatigue of the heart valves, the brain aneurysm simulations.
Do you work with Chang Hao?
Yeah. You know Chang Hao.
I think I have seen some of work by you. Yeah.
Oh, great! Oh, that's a small world. Yeah. We work together.
One conference, I remember something like that.
Oh, I see. Okay, yeah. So when I email you, I definitely say I'm Chang Hao's friend.
Yeah.
Yeah. Nice to meet you.
Nice to meet
you. Can I ask a follow-on question to Yui's question? I'm Nat Trask. I'm at Sandia National Laboratories. I'm curious about the modalities that you're looking at. So when you were describing this diffusion modality, right, that would be a very high fidelity modality, which would probably, I'm not sure what it gives you, like full field strain data or something, but are there, are there lower fidelity modalities available that characterize, maybe it's not enough to fully calibrate a mechanical model, but that correlate with anomalous anisotropy, like you mentioned, or other, like easy diagnostics that could reveal anomalous microstructure, even though it might not be enough to actually calibrate the full-on mechanical model?
There is some other ones that I'm not fully familiar with, like backscattering ultrasound. People have used, definitely lower fidelity, as you were describing, and then optical coherence imaging. But the basically the state of the art for cardiac architecture in vivo is diffusion tensor imaging, and that one is still people trying to improve.
Thanks. Great talk.
Yeah, thank you.
Do we have more questions? If not, thank you, Dr. Reza, for tuning in today and for giving this wonderful presentation.
Thank you very much, and thank you, everyone. Thank you, George, very much for inviting me. That's really an honor to present in this seminar series. So the next talk is started right now?
Yeah, it starts right now.
So I keep it quiet.
Please feel free to be in the presentation. We would appreciate it. Yeah, okay. So our second speaker today is Dr. Sølve Eidnes. He would be talking to us about pseudo-Hamiltonian neural networks for learning partial differential equations. He is a research scientist in the Analytics and AI group in SINTEF Digital in Oslo, Norway. He has a PhD in mathematics from Norwegian University of Science and Technology in Trondheim, specializing in structure-preserving numerical integration of differential equations. At SINTEF, his main research activities have been on time series analysis and forecasting of industrial processes and physics-informed machine learning. With that, please join me in welcoming him. You may want to take it away. We don't see you.
There. Now you can hear me. Hi, do you hear me?
Yeah.
Yes, and you see the screen?
Yes.
Yes, thank you very much, Lotta, for the introduction and for inviting me and giving me the opportunity to talk at this seminar. And thank you to George too, of course. So I will present a very recent work on pseudo-Hamiltonian neural networks for learning PDEs, which is work I've done together with Kjetil Olsen Lye, also from SINTEF. And this is building on work I've done previously with Eivind, Signe, Alexander, and Camilla from the group. And also Håkon Norén, who is a PhD student that I'm supervising together with Professor Elena Sheldoni at NTNU in Trondheim. So I will start with presenting myself a little bit more and telling you about where I'm coming from, academically, that is, because that has influenced what I'm working on now and what I will talk about in this presentation. So I did my PhD, as Sonata said, at the Norwegian University of Science and Technology, or NTNU, and I did it within the field of geometric numerical integration. And for those of you who are unfamiliar with that term, that is structure preserving numerical methods for solving differential equations. And that means structure preserving, typically that you would want to preserve some geometric qualities of the underlying systems, typically the energy, for instance. You have a system that preserves energy, and then you want the numerical method to inherit that property so that it also preserves energy exactly. An example here is given, but the plot on the right-hand side is a double vector system integrated with a method called discrete graded methods, which is a second order method, and is on the left-hand side is also a second order method, but it is not energy preserving, and with long time it will deviate from the path it should stay on, and you will get unstable solutions. And that is one of the motivations for this, having stable methods and good long-time performance, and it also in many cases might be desirable to inherit these properties by itself, that you want this qualitative behavior of your solution. And that is kind of what I want also to bring into physics-informed machine learning and what we're trying to do in the group I'm working in. And I should mention that my supervisors on this was Lena Sheldoni and Brynhild Fovren at NTNU. And now I'm working in SINTEF, which is Norway's largest research institute. It was established some decades ago to bridge the gap between academia and the Norwegian industry. And I am part of the analytics and AI group in SINTEF Digital, which is a quite young group, both in terms of when we were established and the age of the people in it. We are 12 researchers, all permanent. Most of us have PhDs or are currently getting one. And we have roughly these three main research focus areas here, where the one that I've been working on most and a very important area for the group is hybrid modeling or physics-informed machine learning. So we have been looking into pins, for instance, and we will probably release a paper on arXiv next week, a short paper on pins for flow in porous media, but that is, although that's not what I will talk about today. So what I will talk about today is more related to this research project that we recently got funding for, or we got funding for it last year, but it's starting in July. We'll run for 4 years, called PhysML, Structure-Based Machine Learning for Physical Systems. So this is sort of trying to take these ideas from geometric numerical integration into machine learning of dynamical systems. It is a project where Elena Sheldoni, my co-supervisor from the PhD, is the national academic partner, and we supervise a PhD student here. And we are, of course, very honored and happy to have Professor Kanadakis as an international partner in this project. So that's also one reason why I'm very happy to be able to give a talk here today. I hope that you will find what I'm saying interesting. Maybe it will pique some interest in having a collaboration in the coming years. And I'm also, of course, very happy to, if listeners outside of the Crunch group find the talk interesting and want to reach out. So the overview of the talk is like this. First, I will introduce very briefly these pseudo-Hamiltonian neural networks. And then I will take a step back and give the background, looking at work we have done on pseudo-Hamiltonian neural networks for ODEs. Then I will go more into the theory of the new methods. Then I will talk specifically or a bit more about the training of dynamical system models with numerical integrators. And then I will show some results in the end. And please interrupt me at any stage during the talk if you have questions. So these pseudo-Hamiltonian neural networks, they are based on considering a formulation of PDEs, which we call pseudo-Hamiltonian PDEs. And this is the one you see here, and it is a very general formulation because we include a term on the right-hand side, which is very general. And here with the u to the power of j, I mean u and all spatial derivatives up to an arbitrary order. And then it can also depend on the space and time variables. But the clue here is these first two terms, which we want to find models for. So the first term is a conservative term, and the second is a dissipative term. So if you just have this green term, this would be a conservative PDE, which would conserve the Hamiltonian or the first integral h. If we just have this purple term, it would dissipate with time. So the integral v would dissipate. And then we have this extra term here, f, because we want this formulation to be able to model also systems where we don't have conservation or always dissipation. So this term here consists, the conservative term consists of a skew-symmetric operator and the variation derivative of the non-canonical Hamiltonian or the integral h. And this skew symmetry of S ensures that h would be preserved if these other terms are 0. And similarly, the second term there with the R is a positive semi-definite operator, which ensures that V would dissipate with time. And yeah, this work is in this paper with Kjetil, and that is out on arXiv as of today. So please check that out if you want, but I will come back to the results of it, of course. So the idea, here I abuse the notation a little bit because we don't actually model continuous models, but the idea is to model these different parts of this formulation by separable or separate models. So here I use hat to denote that this is models, and theta to denote the learnable parameters that these models depend on. And an example of such an equation could be the forced.
Sorry to interrupt. Can I ask you a question about the model form? So this looks a lot like metroplectic dynamical systems, but without the degeneracy condition. If you neglect the F, you made a comment. So usually you need that degeneracy condition in order to either conserve H or your V, what you have here would be non-decreasing if it was an entropy. You made a comment about dissipation and conservation. Can you point out like explicitly what is conserved or dissipated? Or, sorry, are you familiar with the metroplectic version of this?
I could have noted that it's very similar to metroplectic formulation and also this generic formulation from thermodynamics. We call this pseudo-Hamiltonian to connect it to these Hamiltonian neural networks. In this general formulation, nothing would be guaranteed to be preserved or dissipating because we have this F, which could be anything. So it's more that you have this structure of these terms that you want to learn. And when we are modeling this, which I will come back to, then we are able to separate these different terms into terms with physical interpretations, if you will.
Understood. Thank you.
Thanks. So an example is the KdV-Burgers equation or the viscous Burgers equation. So without this source term F, this is the KdV-Burgers equation. And without this viscous part is the standard KdV equation, which conserves the energy and actually infinitely many integrals of the solution. Here we have these different terms, as you see, in the general equation, where we have up to third derivatives. Well, we still instead consider these integrals, which we can take the variation derivative of. We only have first derivatives in those, which is crucial for the modeling part. So in this case, the skew symmetric operator is the spatial first derivative, and the positive definite operator is just identity, which we denote by capital I here. And then here is an example of how we're modeling that. So we have training data up to time not that far in the future, because there is no time dependency here, so we don't need that far ahead. But we have different initial conditions, different samples, so we get some variation in the training data. And then we model this, and we could have modeled it better, but I wanted to distinguish the model from the exact solution here. So we find this model for the right-hand side of the equation, and then we solve it with a numerical method in time. And then we compare that to the solution obtained by solving or applying the same method to the exact system. And as we see here, we are able to model that quite well. But the crucial part is that we have this separability of a model, so we can take out some parts. So the lower plot here, there we have removed the dissipative term and this F, the force term. And then we are left with a Hamiltonian PD that preserves an integral. And this is actually the KdV equation. So we compare this to the exact solution of the KdV equation, and we see that we are modeling that quite well. And then I will give some more background before I explain the model in more detail, because this builds on Hamiltonian neural networks and pseudo-Hamiltonian neural networks. So I will start by defining what we mean by Hamiltonian ODE systems, because we are looking not just at the canonical case, so we are assuming that we could also model non-canonical systems. So thus we consider general ODE first order systems on this form, which has some invariant H, which typically could be the energy, but it could have other physical meanings, of course. And this H follows this property here, and that means that energy of the system, or this H, is preserved with time. Just we can use the chain rule and replace the left-hand side by this, and we see that this becomes 0. And crucially, with a result by McLaughlin and others, that if you have such an H for this ODE, then you can find an S, which is skew symmetric, such that you can write the system on this form. And this S is generally not unique. And the other way around, if you do have this system to begin with, it's straightforward to see that this is energy preserving, because you can then replace G by S times the gradient of H, and because of the skew symmetry of S, this must be 0. And then this paper by Gredanus and co-authors, who introduced Hamiltonian neural networks some years ago, they only consider the canonical case, where they have even number of states, where Q is generally the position of the system, and P the momenta. And then they assume that they know that the S matrix is this canonical skew symmetric matrix. And then the idea of Hamiltonian neural networks is to model, train a neural network model for the Hamiltonian. So instead of trying to learn the system by training a model for the entire left-hand side, they train it for H, and then they assume that it has this structure. And then it is guaranteed to preserve this learned H. So in the loss function, they compare the output of this right-hand side with the model with the derivatives of QMP, because they also assume that they have data on the derivatives. And then, of course, also here I should mention that there is a paper that looks at this more general case where S can depend on the state solutions, Poisson neural networks by Yin and co-authors, including Professor Kanadakis. And this is then the more general formulation that we also want to use. So building on port-Hamiltonian neural networks, which was introduced a couple of years ago, we consider the class of pseudo-Hamiltonian ODE systems for pseudo-Hamiltonian systems for ODEs. This is very similar to what is called port-Hamiltonian systems, which is a term that comes from control theory, but we do not impose any structure or assume anything about F, which makes it a bit more general. And actually, as for the PDE case, this is very general because F can be anything, so it can model any ODE system. So we need some more structure to actually learn something here. And in this case, we have that S is a skew-symmetric matrix, R is positive semi-definite matrix, H and V are functions mapping from U to a scalar, and F is, as I said, very general. And H, or gradient of H, is the gradient of H, of course, but I put it up here to compare that to the PDE case. So the idea of pseudo-Hamiltonian neural networks is to have models for each of these parts. So here we have neural networks models for H and F, and then we learn in the general case we could also learn S and R as neural networks, but we then need to impose these structures. But in the paper, because this is so general, we need to put some more assumptions on the system. So we assume to know S, although it can be different from the canonical structure. And we assume that R is a diagonal matrix. So we just need to learn the parameters on the diagonal. So an example here from the paper on pseudo-Hamiltonian neural networks is a system of tanks that's connected by tubes. And this skew-symmetric matrix consists of this incidence matrix B, which tells you how the tanks are connected to the pipes. So just the architecture of the system. Then we have this, we assume there can be friction on the pipes, which is then given by this R matrix with friction coefficients on the diagonal. And then we can have external forces on the pipes and the tanks. And then model the system that we modeled is a system where there is a leak, or you say there is a leak in the fourth tank, which is modeled by this case here. And then the crucial thing then is that we are able to model this system while still learning a model for the leak in itself. So the plot on the left-hand side is a plot of the leak in the fourth tank, and we also learn that there is no leakages in the other tanks. And then crucially, we have a model for the system even if we stop this leak. So we have trained it on the system just with this leakage, and we have a model for the system if it continues with that, but we also have a model if we stop it. And the code for this paper is on GitHub, and we also made this Python package, phlearn, which we have built on now with the PDE extension.
Hi.
Yeah.
Can I ask a question?
Yes.
This is Jim from the Crunch group. So from your previous slide, I see you identify FT, but in the formulation, it seems that there is no uniqueness in FT, if I understand it correctly. Maybe I misunderstood it, but could you make some comments on the identifiability or uniqueness of the right-hand side term?
Yeah, that's a good question. I didn't say that, and I should have said that here we assume that there are no external forces on the pipes. So that is 0. And that brings in some uniqueness to this example. But that is generally, this pseudo-Hamiltonian formulation, there is generally not uniqueness in it. So we need that to be able to learn the separate parts. And that is something we continue to work on to try to identify more clearly in what situations you have uniqueness of the formulation. Because in this paper, unfortunately, we don't have a clear definition or explanation of that.
Yeah, thanks for the clarification.
So this slide here is the PDE analog.
Can I ask another question about your tanks? So you say there's the incidence matrix there. Is there any comment that you might want to make about the underlying physics? Like there's a connection between the incidence matrix and the gradient, the integral of the gradient operator. Like, are those B's just, can you make a tie between that and a physical model? For example, like a hydraulic network or something like that? Or do you just, what's the intuition there?
So the incidence matrices B, they are explained, or they tell you just if either tank or pipe is connected to one or the other of what of the other tanks and pipes is connected to. So I don't know if I understood the question, but it is. I mean,
for example, the difference in, you know, you have like the volumetric flow rate is tied to the pressure difference between adjacent tanks, for example, would be something you could derive from Passet flow. Is there any connection there? You commented on getting an interpretable leak at the outflow, but like, where do these B's come from, and do you see a physical connection?
Yeah, I mean, when you derive the equations, you do, as you say, you look at the pressure differences, and you can derive this equation from that. And it's but it's a good question, because it's not super clear how we could assume that we have this structure if we don't know anything about the Hamiltonian or the energy of the system, which is what we want to learn. So it is sort of a, and I don't have a very good answer, I'm afraid, because this is a test example where we show that it works, but it's not very clear if it makes sense to say that we have these incidence matrices without actually deriving those from the physics. And in that case, we would also have the Hamiltonian, of course.
Okay, thank you.
So these are the what is called non-canonical Hamiltonian PDE systems. This is maybe a term that's not everyone would use, but we base this on the book by Leimkuhl and Reich, at least, where we have, similarly to for ODs, we have some integral or invariant of the system that is preserved along the solution. So that means here that we have some what we call Hamiltonian or first integral. We could call it first integral, which follows this property here. And here we use the variation derivative or functional derivative instead of the gradient in the OD case, which is defined as so. And the preservation property of this follows also directly by the chain rule. And similarly, as for the ODE case, we have this, that if we have a Hamiltonian or a preserved invariant of the system, we can find a skew-symmetric operator S, skew-symmetric then with respect to the L2 in the product, such that we can write this ODE on this form here as a skew-symmetric operator applied to the variation derivative of H. And again, also here, the reverse is more obvious. If we insert this for G here, we have as the direct result or the skew-symmetric property that this must be 0. to find a model for this, we have data in discrete in discrete space and time, and we need to start by discretizing in time. So we say that we have some discretized first integral or discretization of the first integral or Hamiltonian H, and then we approximate the skew-symmetric operator by a skew-symmetric matrix, by a matrix SD, which is not a skew-symmetric matrix in the classical sense, but is skew-symmetric with respect to the discrete inner product, which we define as a discrete version of the L2 inner product. And then we also define the discrete analog to the variation derivative by a similar or analogous property to the variation derivative in the continuous case. And then we have this relationship between this discrete variation derivative, which is consistent approximation of the variation derivative, and the gradient, which is that if we do a weighting that depends on the discretization parameters, kappa, we have this equivalence between those. And then we can also do a weighting of this matrix so that we get the matrix SP, which is skew-symmetric in the classical sense. And then we have that the spatial discretization of this full pseudo-Hamiltonian formulation is given by this case here, which we then can equivalently write with, instead of variation derivative, we can use gradients. And instead of these skew-symmetric operators, we can use skew-symmetric matrices. And there you probably see right away that if we set V to be equal to H, we get a pseudo-Hamiltonian system of ODEs on the same form as we used in the PHNN paper results for ODEs. And it wouldn't be a big challenge to extend the pseudo-Hamiltonian formulation for ODEs to be on a form like this. But it would be a bad idea to use the pseudo-Hamiltonian new networks for this formulation directly, because then we would disregard, of course, the structures that we know to be present in these integrals, H and V, because we know that these are discrete approximations to integrals over time. So as an example, we can go back to the KdV-Burgers equation. And if we don't look at the external force for now, we have these integrals H and V, which we can approximate by quadratures, sums over the spatial points. And here we see that if we use just first order forward approximators of the derivatives, finite difference approximators, that is, then when we take the gradient of these approximated integrals, we still get approximations of the variation derivatives that are second order in time, because we get this second order finite difference approximations because of the cyclic behavior of these approximated integrals. And I did not mention that we assume that we have periodic boundary conditions here, which is crucial for this result. And then we have this relationship between the discrete variation derivative and the gradients by a weighting by the step size in time h. So as for the OD case, this pseudo-Hamiltonian formulation is very general, and it is not unique. So if we want to learn anything here, we need to impose more structure than this. So what we assume is that this skew-symmetric operator S is constant, and R2 is constant, so they are not depending on the state. And we also assume that R is symmetric. And we say that F is independent of the derivatives of U. And then furthermore, to be able to model more general systems without needing to approximate very complicated operators, we let A we have symmetric positive semi-definite operator that commutes with R and S, and we multiply the system by this from the left, and we get this form here, which is what we use in the paper. So here S, this new S is still skew symmetric, and this new R is still symmetric and positive definite. So then we discretize in space, as explained in the previous slides. And we arrive at this system of gradients and skew symmetric and positive definite matrices. And here I just, this was just going away from using boldface for vectors, which I used in the previous slides. So in the rest of the talk, I will not use boldface, but from now on, I will assume that we have done spatial discretization. So U here is a vector of the spatial discretized U. And then the idea is to model these different parts of this formulation by different models. So we have models for these operators A, S, and R, or matrices after the discretization. And we have models for the Hamiltonian H and this dissipative integral B. And we have a model for the external forces. So the full PHNN model for PDEs, or the class we are looking at, is then given by this form, where the right-hand side is a combination and a sum of different parts. So these operators, they are modeled as trainable convolution operators to approximate finite difference approximations of derivatives or of the operators that are present. And we let K1, K2, K3 here denote the kernel sizes of these convolution operators. And H and V, they are modeled by convolutional neural networks, where we have 3 layers and a kernel size 3 on the first layer. And after the last layer, we do a summation so that we get a scalar output. And this way of doing it is very inspired by this paper by Matsubara and co-authors, which, as far as I know, is the only paper on extending Hamiltonian neural networks to PDEs. I might be wrong there, there might be others out, but this is what I've seen. It's a very interesting paper, which also introduces a discrete analog to the automatic differentiation algorithm. And they study purely Hamiltonian systems and purely dissipative systems. So they do not consider this more general class. So we also have this F, and we also use we use a convolutional neural network here with just kernel size 1, because we don't assume to have spatial derivatives of U in F. So before talking more about the temporal discretization, I will just note that we have this connection between convolution operators, as in convolutional neural networks, and the finite difference approximations of spatial derivatives. So that means that to model second derivatives or approximations of second derivatives, it is sufficient to have a kernel size 3 on the first layer of the convolutional neural network, or of the convolutional operator that models these operators A, R, and S. And if we were to model it by a baseline model, which is what we compare to in the paper, we have, for instance, for the KdV equation, we have third derivatives, and then we would need a kernel size of F. So that would that complicates the model. Or said in another way, using this pseudo-Hamiltonian formulation simplifies the neural networks. So before showing the results, I will talk a little bit about.
Yeah. Before you move forward, you said that the learnable convolutional stencil for A, I think it's on slide 22. It needs to be invertible, right? In order to, so how can you guarantee that that's invertible?
In this formulation, it will be invertible, but we don't actually. We never invert it, because we look at this system here, And then we say that this model is X, G, because we say that we look at the more general form, but actually we make it more general by multiplying by A on the right hand side. Oh, no, from the left hand side, right? To compare it to a baseline model where you don't do this, it would have to be invertible if the baseline model should be able to learn this. But we are able to learn it even if it's not invertible, because we use actually this formulation when we learn it, if that makes sense.
Right, but if it doesn't have full rank, you could have a degeneracy and the solution could, you wouldn't be able to fit to the full vector of U's, right? Is that the right picture? It makes sense, just trying to track. Yeah.
Yeah,
okay,
no,
great.
that's correct, yeah.
Thanks.
Thank you. So yeah, I will talk a little bit more about how we do the discretization time and how we do the training. Because as I said, when I talked about this first paper by Gredanus and others on Hamiltonian neural networks, they assumed that they know their derivatives, which we do not want to do. So then there are papers who do integration in the training. So they learn the model at each step, at each epoch, and then integrate and compare it to the future states. And then they, of course, they can do several steps, but the drawback is that they would rely on an explicit integrator, because it would be very expensive to use an implicit integrator in that case. So what we do is the same as what is done in this paper by Matsubara and others, and also in the paper SympNet on symplectic neural networks by Kanadakis and others, that we train on the integrator, which means that we feed the data to an integrator. So if this phi here is the forward Euler method, for instance, this is just G hat evaluated at UN. But in this case, we can use implicit integrators, or more specifically a subclass, which are mono-implicit, in that they depend explicitly on the solution in the current step UN and the next step n+1. And that means that we can use a much wider class of integrators, and integrators with better properties than purely explicit integrators. So for instance, we can use the implicit midpoint method, which also others have done. Or we could use this fourth order symmetric but not symplectic method that we introduced in the paper on PHNN for ODEs. And the cost of this method when in training is dominated by the evaluations you have to do of the vector field or of the model G. So this is the fourth order method is roughly 4 times as expensive as the implicit midpoint. But I want to note here that the implicit midpoint is as expensive as forward Euler. And this fourth order method is not more expensive than the classical Runge-Kutta method. And when we do this, when we actually take in more than just 1 point, of course, the advantage is that we will even out the noise in a way. So if we use the implicit midpoint method, we have directly, if we have normally distributed independent perturbations for this example, then we reduce the variance by a factor of 2 compared to using any explicit integrator. So these are some results from the previous paper on ODEs, where we have tested out these 2 methods and compared them to methods that are comparable in cost. So the forward Euler and midpoint methods are equally costly, approximately, and the same for RK4 and SRK4. SRK4 is this symmetric Runge-Kutta method that we introduced. And here we see that these symmetric methods handle noise much better than the explicit methods. And also, if you have a large step size between the points, then you need a higher order methods to get accurate results. And then Håkon Norén, who I mentioned as a PhD student that I supervised together with Elena Geldoni, has looked more into this and also found or identified this class called mono-implicit Runge-Kutta methods, which have been studied in other cases before. but identify this as a very useful class of Ronkuta methods to use for training of these models. And if you have sparse data, large time steps between them, then you get a lot of gain out of using higher order methods. And they're not that expensive either. So this monoimplicit Ronkuta methods of order 6 needs 5 evaluations of the model. So it's just a little bit more expensive than the classical Ronkuta 4 method. And there is code for this work that Håkon has done on GitHub. Here are also some bar plots that shows similar results. So then I will come to the numerical results for PDEs. I will show 3 different examples, starting with this forced KdV-Burgers equations, which I also showed some results for in the beginning. So here, the skew symmetric operator, as I said, is the spatial first derivative, and both A and R are the identity here. And these plots, here we have trained up to time 2. So we see that we get quite accurate models up to time 2, and then we don't get, or the models start to deviate from the exact solution beyond that, because we have here external force that is also depending on time. And of course, the neural networks aren't able to approximate this F beyond the domain of the training data. But we see here that we get quite accurate predictions, although the baseline is also good in this case, and it's better than the most general PHNN. So, and that I should say, the general PHNN model here is the model that I presented, where we assume that the kernel sizes of the operators is 3, and where we assume that F can depend on either state, space, and time. So that is a model that can be used to model all the examples that I will show here. While this informed model, that is informed of how the operators look, so it doesn't need to learn that, and of whether or what variables F depend on. So here we see that it is more difficult to model the system when we have this general model. But we have the same feature here that we have for the OD cases. We get separable or a separate model for the external force. And here we also have a separate model for the dissipation term and the conservative term in a way. So for this baseline model, which is just one neural network, which models the entire right-hand side, we have also found the force by, in this case, because the force is not depending on states, so we just subtract the model where the state is set to the 0 function, and that was 0 solution, and that works in this case because the right-hand side is 0 in that case, and because F is not dependent on the state, but in general that wouldn't work. But we see that when we have this information, it outperforms the general PHNN model, which doesn't have this information. But the feature of the PHNN model, of course, is that you can separate these terms, so you can remove the force, but you can also remove the viscosity. So here we have modeled this system on the top row. We have a model for the force, we have a model with the force removed, and we have a model with the force and dissipation removed, in which case we have the standard KdV equation. And what we see is that these PHNN models are, the best of them are good, but they are very sensitive to different initializations of the parameters in the model. So this is, here we have included, here we have the average of 10 different models, and we have included the standard deviation. And there we see that the standard deviation is very high for the general PHNN model. So in practice, if you have this general model, it will be a good idea to run several models and then pick the good ones. And of course, you wouldn't be able to compare to ground truth, but you can pick out those that deviate a lot from the others. But yeah, and I can also say at this point that we see this as because we have this structure of the model, which is kind of, you can incorporate different priors. So we see this as something that used in an iterative process, where you start maybe with a general model, you learn more about the system because you have these different paths where you can have physical properties that you can identify, and then you can inform the models more, and you can hopefully end up with something more similar to what we have in the middle here. So this is a similar equation, or is was introduced as an improvement of the KdV equation, the Benjamin-Bonner-Mahoney equation. We have a source term that is dependent on U as well. Here we have an operator on the left-hand side, which is different from the identity. And here we have much more trouble learning this with the baseline model, which models the right-hand side by one neural network. So here we see a great improvement on using also the general PHNN model. And we have also included a term here where we do not, or a model where we do not have a dissipative term, because we do not have that in this system. But as for the KdV model, we see that it is very sensitive to the initialization of the model, parameters, or the trainable parameters. So here we also have the average over several models and standard deviation. But the informed model is quite stable. And then the last example is a dissipative PD, but with a source term. And this is the Perron-Malik equation, which is developed for use in image denoising. So here we have that this S operator is 0, but the other two are the identity. And here we have generated not much training data, just 20 data points. So at time 0 and time 0.02, which corresponds to the initial noisy image, if you will, even if you just look at one dimension here, and one where this is smoothed out, but it is also affected by the external force. And this point here is that here we have quite large time steps, so here we needed a fourth order method we found, because we see that this, with the midpoint method, it is quite noisy, the model, compared to the exact solution. And this also outperforms the baseline model quite a lot. So here we have the solutions at time 0.02 for the 3 different models. And then we learned also this external force, and we can remove that. And we have this denoised image, one-dimensional image from the models, which is quite similar to the exact solution. So this paper, which is out on arXiv as of today, is an introduction of these models, and there remains a lot to be studied about them. We have not, we have tested on noise data, but we have not included that in the paper, just for it to be easier to compare to the baseline without being affected by noise. And then we have not actually studied the problem with the spatial discretization, because they generated all the data with the same spatial discretization as we can find by the model, because we use the same grid in the model. Although we have a result on this in the paper where we compare to a test where that's not the case. And then we will also want to make these models, this discretization invariant in general, although they are, for instance, so for the BB, no, for the for the BBM equation, where the Hamiltonian is not dependent on the derivatives of U. So that is a feature that it has over the baseline model, that in that case it is discretization invariant, and we would like to make that feature more general. And then of course also we would like to look at extensions to higher dimensional PDs. So the paper, as I said, is out on arXiv, and the code is on GitHub in the same repo as the ODE code. And there are several notebooks that you can check out for the different PDs that we study in the paper. And this is also the Python package phlearn is updated with the models for PDEs. And that was what I had to present. And I'm happy to take questions if you have more of those. Thank you for listening.
Thank you.
Thank you very much, Sølve. It's good to have you here, and good progress since last time.
Yeah, thank you.
And maybe Jen Zhang has questions, more questions, Jen, or not? Jen is the author in that in those papers that you cited, Sølve. Paper, so Jen, maybe you can identify yourself, turn on your camera and say hello.
Yeah. Hi, this is Jen.
Hi.
From Crunch Group. Yeah, I think I have already asked my question, so I don't have further questions at this time, but I think I will read this paper and connect with you after this.
Yeah, great.
Jen, you have one. Sølve made a comment about Hamiltonian systems and PDEs. You have an example in the paper on the Poisson system, where we have PDEs there.
Yes, that's a Schrödinger equation.
The Schrödinger equation, yeah. So you may want to look at that, Sølve, because we use the Ablovich scheme, and it's kind of nice to discretize. It's a consistent discretization scheme.
Yeah, I may have missed that because I've found it a bit surprising that there's not more to find on extension of Hamiltonian new networks and similar methods to the PDE case.
Yeah,
look at that.
The difficulty is, of course, if you have a lot of points. I don't remember how many dimensions, because that becomes like a dimension, right? Every nodal point. How many? What was of the order of 60, 80 points? How many points did you have, Jen, in that?
It's 40 points.
40. Okay, yeah. So at some point you will hit the ceiling with this.
Yeah. I have used generally one of the
convolutional piece, right? Because you have weight sharing. I think that's the trick that you use that let you bypass the explosion in the dimension of the degrees of freedom. But if you wanted to go past a finite difference grid, you would hit that same wall, right? In terms of the scaling for the PDE. I had a quick question about forecasting and out of distribution. So, one of the main things that people are interested in the structure preserving stuff is that you would hope that for long-term forecasting out of distribution, by conserving whatever the invariants are, you might get some sort of generalizability beyond what you would get with something like a neural ODE. For the actual structure preserving stuff, it's clear how that argument would go, but for the pseudo-Hamiltonian one where you don't actually have it's not nailed down to an actual energy. Do you see that same kind of thing, or have you done those kinds of experiments?
Yeah, we have observed it. We haven't done like thorough experiments, which we could report on in the paper, but generally it seems to be more stable than the baseline models we have compared to. So for instance, I said that it's very sensitive to the initialization of the new network, but once you have found a good model, it behaves very well with a long time compared to this baseline model. So it appears to have much better stability properties, but this is something that we need to study further.
But of course, for out of distribution, right? Have you done experiments looking where you run your learned model past the final time that you used in the training data set?
That depends on whether it's depending on time. If it's depending on time, then there's not much use in doing that. But it's, explicitly depending on time. But if not, it seems to work very well. We don't need to a lot of data in time for most of the cases. It depends a bit. The most challenging thing is separating out the external force if that depends on state, especially from the dissipative term, because it's generally not unique how you would separate the dissipative term and the external force, even if that's not a dissipative. So then you generally need more data. But if you have an external force that's not depending on the state, then we don't need much data in general, I would say.
I have a quick question. This is Dr. Abdul Khalik from Middle Tennessee State University. Thank you very much, first of all. It was a very good talk and very informative.
Thank you.
PEINN is going everywhere, right? We are trying self-adaptive PEINN as well, and to capture the shock and things like that. So my question is, like you mentioned, if the source term is non-linear, for example, what could be the effects of that one? You know, in your experiments, it's always linear, right?
Yeah, well, we have this sign terms. I mean, it's
sign...
depending on x on sign, so it's a linear function of u. That's true.
So will that non-linearity have any impact? I mean, serious impact, or just because it could be stiff, for example, stiff non-linearity?
Yeah, that makes it more challenging. Yes. We haven't tested that out, so I don't have a good answer, I guess. It's something we should test out in the future. And yeah, one of many things to explore.
In that case, maybe the mono-implicit Runge-Kutta methods will be more helpful.
Yeah, absolutely. I do believe that this is also something that's very interesting. I didn't talk that much about that, but this PhD student Håkon Norén at NTNU is part of this group there, which has a very good background on geometric integration, and I think that this is something that's very promising in learning of dynamical systems.
Right. Thank you.
Thank you.
Maybe I think there's on Sølve, there's on the chat there is a paper suggested by Tom Bertalen. Tom, if you are still listening, you can ask your question. Or there's a suggestion about a paper that they have written, learning Hamiltonian systems from data. Maybe he signed out. Can you see, Sølve, can you see the chat?
Yeah, I clicked on the link. Yeah, I see it's Kyriakidis. So I have not studied this paper, so I will do that.
And maybe Matthias has a question. We want to be the multinational today.
Yeah. Hi, I'm Matthias from Germany.
Yeah, hi.
So it was really a very nice talk, very impressive, very. I learned a lot. So my impression was that your pseudo-Hamiltonian approach it's quite close to infinite dimensional Porte-Hamiltonian systems. I mean, just without the ports. And there's a lot of literature. I mean, there are even books of Zwart and Jacob on infinite dimensional Porte-Hamiltonian systems. So can you somehow have some benefits from this existing mathematical theory?
Yeah, absolutely, and that's something we have been trying to understand. It's because it's not a field that or something that those who have worked on this is that familiar with. I know you are one of the experts in the field, and we are trying to see what more we can benefit from the vast literature on Porte-Hamiltonian systems. Yeah, and I believe I will see you in Poland this summer at the municipal.
Yeah, we'll see. And,
so then we can discuss this more.
Yeah, or maybe you can include the ports to your approach.
Yeah, absolutely. But the one reason we haven't done it is because we don't feel we understand that sufficiently, actually.
Okay, thanks.
Thank you.
Some data is, do you want to have Kasia say hi to Sølve?
Of course.
Kasia is sitting next to Sølve to some data.
You want to come here?
Sure, I can.
Yeah.
Oh, well. Hi.
Hi.
Yeah, I'm glad that you could present at our group.
Yeah.
My group can present at my other group. It's very nice to have that connection strengthened.
Yeah. Thank you for facilitating.
We're all a big family. All big family. It's common interests. It doesn't matter where we are from. Any other questions for Sølve? You know, Sølve, I find fascinating always with the Scandinavian speakers. They are the most honest speakers in the world. Let me say that. They would not commit to anything unless they have tested, which is very nice for a researcher to have. So thanks for enlightening us today, and take care.
Thank you, and thank you for letting me present there. It's a great opportunity and great honor.
Some data, but back to you.
Thank you, everyone, for tuning in today. And thank you for both the speakers for the wonderful talks. So we end our Crunch seminar here today. I would be uploading the the recording on our YouTube channel. Please follow us over there and have a great rest of the day and a great weekend ahead. Thank you. Bye.